Hello, as requested by some of you, today we're going to do a tutorial on how to do a self-driving car using our lib plugin and package in Unreal Engine. First, we're going to do a quick overview. Currently, Unray has a plugin designed for Unreal Engine version 5.3. And it has another part in Python, which is a package used to design and create agents with RLib. This is the basic structure that we're going to see for now. In future videos, we're going to see more features from Unray and RLib. Okay, on the left side of the graph, you see the Unreal Engine plugin, which inside has all the settings so you can create and configure environments and agents. It also has a connector plugin, so you can talk to the Python package, which inside has a wrapper that contains RLib and all the components, so it can talk to the Unreal Engine plugin. And so you can do the training directly inside of Unreal Engine. So that's the quick overview. The goal of this tutorial will be to create a car that navigates a track and gets as far as possible without hitting the wall. For the actions, we're going to use multi-discrete. It's a data type made by RLib. You can see more information on their documentation. And then we're going to have two types of actions, turn left or turn right. For the observations, we're going to have 7 raycasts pointing in several directions. The reset states are going to depend on on the step count and if the car hits a wall. And the rule word is going to be if the car is going in the middle of the track. So that's the general idea. Now we're going to start by creating a new Unreal Engine project. We're going to use the games templates and vehicle. We select folder and set a name. Now we run it just to make sure everything works out of the box with WASD. See, it works fine. Next, we're going to install the Unray plugin. So you go to the Epic Games Marketplace. We're going to search for Unray. Okay, here you see I already have it installed, but you'll have the option to add it to whatever engine version you want. Right now it's 5.3. But yeah, you can install it from here. Now we go to the editor, edit plugins, and we search for Unray. After it's installed, you should see it up here. Now you can enable it. It's going to tell you that it's in beta version. You can click OK, and you need to restart the editor. We can check again, make sure it's enabled. We see it's enabled. And that's all we have to do on the Unreal Engine side. Now we're going to go through the setup of the Anaconda environment. You could use any other type of environment like pip, but we recommend using Anaconda because we think it's more convenient to create the environments. So yeah. So for that, we open the Anaconda prompt and create a new environment. I'm going to say yes, and then we enable the virtual environment, Conda activate, and then the name. Now that it's enabled, we are going to install Torch and RLib packages. Here I already had them installed, but it might take a few minutes for you because of TensorFlow installation. Next we're going to do pip install Unray. Because it's a smaller package, it should take a smaller amount of time, and that should be it for our environment setup. Okay, now we're going to go back to Unreal Engine, and now we're going to set up the car. First we are going to open the parent class, which is vehicle ADV pawn. Here we have the inputs for our car movement, and also we're going to open another class, sports car pawn. Now we go back to the parent class. We're going to copy the set throttle input with the vehicle movement component and the set steering input. We copy those and paste them into the sports car pawn event graph. We're going to create a custom event. We'll call them custom inputs. The reason we do this is so we have a continuous input in the car throttle. The steps will generate an input, but it will have problems moving. It will seem as it jumps all the time. So that's why, and we'll make the agent control the steering of the car. Now we're going to create two variables for the throttle. We're going to promote it to a variable and name it forward. And also for the steering, we'll promote it to variable and we'll name it side. Now to be able to use these custom inputs, we're gonna set up an event tick, and from that event tick we call our new custom event. Now you'll notice that if you hit play, you won't be able to move the car with the WASD keys. That's because we have overridden the throttle and steering inputs with our custom event. Now in order to test if you want to be able to move the car using the keyboard, we're gonna copy these two events, enhanced input, throttle and steering. We're going to copy those from the parent class and paste them in the child class. So for the throttle, we're going to set the forward value to 1 when it's triggered. And when it's completed, then we're going to set it to 0. Similar thing for the steering. Now for the steering, we do a similar thing, but we use the action value directly, so it gives us the left and right inputs for the triggered and completed flow. Now you'll notice that if you hit play, you can control the car movement with the keyboard, and in any case we recommend you disable the inputs from the parent class just in case, so you avoid any conflicts. Here you can see it still works, but yeah, just in case. Now we're going to configure our car sensors. In this case we're going to use raycasts. We're going to set them up in front of the car so it can detect the walls. So we're gonna add a new component to the mesh. We're gonna call it arrow. Now we're gonna duplicate it 7 times, so we have 7 directions. In order to make them easier to see and to manipulate, and so they don't detect any collisions with the floor, we're gonna move them up a little bit. We're going to set the X location to be in front of it, about 230 units, and the Z axis to 60. And we're going to set the color to yellow. You can choose any color you like. And we're going to set directions from minus 120 degrees to 120 degrees with 40-degree intervals. Now we're going to set up a new function. We'll call it trace arrow. Now we're going to add a new line trace by channel. Its input will be an arrow component. And we're going to set up a length component so we can control how far away the line trace will see. And for the returner, we're going to return the distance at which the line trace detected the obstacle. Now we're going to use two things from our arrow component. First, we're going to get the world location. And also we're going to use the forward vector, so we have a vector in the same direction as the arrow component. We're going to hook up the world location to the start of the line trace, and for the end position we're going to add to that start position. We're going to multiply our forward vector because it's a unit vector, so we multiply by a constant, and we add it to the world location, so we have a vector pointing on the same direction. Here we can set up a different color. You can choose any color you like. Here we're going to break the hit result, and we're going to return the distance at which the hit was made, and return that. And that's all we need for the sensors. Now we're going to go back to the event graph, and we're going to set up a custom event. We're going to call it trace arrow. Now we're going to take our 7 arrow components, we're going to drag them to the event graph, and we're going to make an array. We add 7 pins, and we connect each one of the arrows to one of them. In this particular case, the order of the arrows doesn't matter. And now we're going to loop through each one of the arrows, and we're going to, for each element, we're going to call our function trace arrow. We're going to set a length of 8,000 units, and for the arrow we're going to use the array element. Now we're going to create an array of observations. We're going to call it total observations. This array will be sent to Unray, and Unray will send it to the Python package, and it will be used during the training process. So those will be the observations for our RL agent. So to return, we're going to set our total observations to be an array of 7 elements, type float, and those will be the return values. We're going to loop through all of our outputs, and the distance will be each one of the values, and the index will be the array index. Now we're going to connect this function to our event tick, so it's constantly sensing and giving inputs about the environment. Okay, that's hooked up. Double click to make sure that we are calling the custom event and not the function. Now, as you can see, our car has the tendency to flip over if we make sharp turns at a high velocity. So to handle that, we're going to go to our sports car pawn class, then to components, then vehicle movement component, and we're going to change its settings so it doesn't go as fast. On the right side, we're going to look for mechanical setup. Now under engine setup, we're going to change the max RPM to 4,000. Now our car is not going to move as fast, and it won't flip over if you make sharp turns. Now this is an extra step. You might skip it if you want, but this is to improve the measurement precision. So what we're going to do is we're going to add a scene to our sports car pawn, and we're going to put all the arrow components inside of the scene. Now we're going to go to the event graph. We search for the event tick, and we're going to make sure that the scene is always parallel to the floor. So in order to do that, we're going to take the world rotation of the scene. We're going to break it up, and we're going to make sure that the only axis that rotates is the z-axis. The rest we're going to set to 0. So this way we guarantee that the sensors are not going to tilt with respect to the floor whenever the car steers to the left or to the right. Now we're going to do something important. We're going to set up our track so the car can recognize its edges. Right now, if you go to player collision, you'll see that the track doesn't have any collisions around its edges. In order to do this, we can take advantage of the fact that the track is made with terrain spline, so we can use that. Go to selection mode, we're going to select landscape, go to manage, splines. Then in the details tab, you're going to look for segments. And under spline meshes, we're going to select the first one that we see. Here you can double click it and it will take you to the mesh. Now we're going to add 2 collision boxes. After setting up the collision boxes and saving them, we can go back to the player collision, and you'll notice that now we'll have box collisions around our track without manually needing to add collision boxes. Now if you hit play, you'll notice that the car will collide with the borders of the track, and the line trace will detect those collisions. Now we're going to set up the reward step, and it's done for our agent. So first, what we're going to do is we're going to go to our sports car pawn. Now if you haven't enabled the plugin content, you're going to need to change your settings, go to show plugin content, and you'll be able to see the Unray plugin contents. Now we go to the Unray content folder, go to blueprints, and we're going to look for our BI agent. It's an interface that we need to implement in order to communicate with the Python plugin. We're going to go to our class settings and add that interface. So we're going to look for BI agent. If we compile, we should be able to see it. We open interfaces, and then you have the functions that we have from that interface. We're going to start with the step function. So from the step function, we're going to get the list of actions. There's going to be an array of type float. We're going to do get and get the element at position number 0. Our array will only have one element, so we'll use position 0. For the forward input, we're going to set it by default to 1. This is so after the first step, the forward input is always set to 1. This is in order to make things simpler. If you wish, you can change it so it's more complex. You could set it up to use more actions and more observations. Okay, now for the side variable, we're going to convert the action value into an integer, and then we need to map it. So the action value will be between 0 and 1. We need to map that to the side to be between -1 and 1. So in order to do this mapping, we're going to use a select. So for the option 0, we set it to -1, and for the option 1 to 1. So if we get a 0, we turn to the left, that would be -1, and if we get a 1, we turn to the right. Now we're going to set up a new variable called count, so we can keep track of the number of steps. The number of steps that we've made so far during the iteration process. So at each step that we make, we're going to add 1 to that counter. So we have control over the number of steps that we want to use. Okay, that's all for the step function. Now in order to detect collisions, we're going to set up a new event. We're going to set up a custom event and we'll name it collision. In our car class, we're going to add a box collision, and we're going to set the dimensions to the following. So for the location, we're going to move it forward 20 units and up 80. And for the scale in X, we're going to set it to 9 and Y to 4 and Z leave it at 1. This is so we can detect collisions on the sites. For the collisions, we're going to set it to ignore the vehicle so it doesn't detect our own car. Now we bring our box collision. From it, we get all the overlapping actors and we promote those to a variable. From here, we're going to remove our own vehicle. It might detect it in some other way, so we need to make sure to remove it. We get a reference to self and we remove it. Now we check if the length of the remaining element is greater than 0. Then we're going to set a new variable that we're going to call hit. Our hit variable will be type boolean. Now we're going to set it to true if we collided with something else and to false if we didn't. That's all we need to check for collisions. Now we'll go back to our event tick and we'll call that function. Could be at the beginning or at the end. We'll add it at the beginning. And just to make sure that the collision detection is working, we're going to add a print and we're going to print our hit variable. Now you can see it's printing it. If you don't want to see that many prints, you can add a tag to it. We're going to just put hit. And you see that it's only there once. And when you hit a wall, it changes to true. We're going to use this hit variable in order to know if we've hit a wall, and in case we do, we restart the training. Now we're going to go to our getState function. This function will be used by Unray to return the status of the environment, and it will be used to make the decision of what the next step is. We take our total observations and we return it. That's all we need. Next, we'll do the isDone. And we're going to set up the actions that will tell us when our agent will be reset. So our agent will be reset in either one of two cases. First one is if the number of steps is over 4,000, which is a large number, or in case we hit a wall. Any of those two conditions will make our agent be reset. Now we're going to set up our reset event. We're here. For this, we're going to go to our parent class. And we're going to look for the reset event on the, if you scroll down, you'll see the enhanced input reset. So we're going to borrow that. We're going to set up a custom event. We'll name it reset car. And we hook up this custom event to here. And this, what this will do is it will reset the car to its original position. Now, to get the position that the car starts in, what we're going to do is, after you hit play, you can do F8 or click on this icon and select the car, and then you can see the original position. You can copy these values and put them into the transform. We disconnect the getActor location and manually put in the original position values. Now we set the rotation, we disconnect it and we set it to 0, so it starts without any rotation, no matter if the car was steering when it was reset. And if you want to test it out, you can hit play, and the event is bound to the backspace key, so you can press that key and it should reset to the original position. Now we need to bind this to our reset event. So whenever the agent resets, we reset the position. So what we're going to do is we connect this to the reset car function. And whenever our car is reset, we're going to change our hit variable to false. And also we're going to reset the number of steps to 0. And now we'll introduce a new variable that's going to represent the reward that we'll give our agent to tell it that it's doing well. Right now we're going to set it to be a float. And whenever the car is reset, we're going to set it to 0. We'll see more of this in a moment. So whenever the agent is reset, we reset all these three variables. Next, we're going to do the get reward. Okay, so we have a set of line traces that measure the distance between our car and the edges of the track. And what we want to do is we want to keep our car as far away as we can from the edges. So what we want to do is take all these distances, pick the smallest one of them, and keep that minimum as big as we can. So we need to maximize the smallest amount that we have between the car and the edges. So in order to do that, we're going to go to our total observations. We're going to loop through all of them. We need to check if each observation is greater than 0. That means it detected something. If it doesn't, then it's 0. So if it's greater than 0, that means it detected something. We're gonna try to use that distance, and to get the minimum distance, we'll set up a new variable. We'll call it min distance. So that's going to be the smallest distance between the car and one of the edges. And at the beginning of the loop, before the loop, we're going to set it to a big value, so that initial value will always be greater than the observations. We'll set it to 10,000 since our line traces only go up to 8,000. Now for each of the elements, we're gonna compare that and take the smallest one of the two. So we're gonna take the current one and compare it with the current minimum distance and take the minimum of the two. And so each time that we compare, we pick the smallest distance. And then if we detected something, we measure that distance, and if it's smaller than the smallest one, then we use that one. And after we go through all the observations, we'll end up with the minimum distance out of all of them. Now we're going to take that minimum distance, we're going to normalize it by dividing it by 1000. And we're going to set the variable value to this normalized one. Now we're going to use this minimum distance to set our reward. But first, let's print out this value so we can see a bit better what's going on. We're gonna return the minimum distance just so we can see it. Now we're gonna go to our event graph. Now please remember to remove this part, otherwise you're gonna get some errors. So now we're gonna get our the value for our minimum distance. That's coming from the getReward function, and we're just gonna print it out, and we'll see how it looks. We'll change the color and set a key, and again we'll highlight it so you remember it's just for testing. We need to remove this later. Okay, now we'll save this, and when we run it, we'll see the reward value printed out. Let's see if I can maybe use a better color. There we go. Now, as you can see, if we drive closer to the walls, the reward will get smaller. It will go to 0. If we drive through the center of the track, it will increase. And yes, as you get closer to the walls, the value will drop down. Now, going back to our reward, instead of returning this raw value, what we're going to do is check if our minimum distance is greater than 0.4. If it is, then we're gonna give it a positive reward. That means the agent is driving through the center of the track. And if it's not, then we're gonna do a negative reward. That means it's going off track. Now we add this to the reward. Then we set the reward value to this new value, and we return that at the end. And now we disconnect our testing function. Okay, now that we have our state is done, reset and step functions, and the reward, we can work on our Python file so we can set up our training. Before that, there's one last important step. We need to set up our connector so we can communicate our agent with the Python package. So we're gonna need to reference our connector for a single agent, this connector _SA. We're gonna need to reference it to our car. So we're gonna drag it to the into the map. Right now, the vehicle is being spawned whenever you start or when you hit play. So what we're going to need to do is we're going to need to drag it into the map because we need a direct reference to hook up our connector. So we're going to use the sports car pawn, drag it into the map, and set the auto possess player to player 0. So whenever we hit play, it automatically uses that instance. And we can use that to connector to our, or to bind it to our connector. So we select our actor agent to be the vehicle that we just dragged. Okay, now we can work on our Python file, but yeah, remember this part is important. If we don't set up the connector correctly, then Unray won't be able to communicate with our agent. Now we go to our recently created Python file named car tutorial. It's an empty Python file. Right now I'm using PyCharm. If you want to, you can use whatever IDE you're more comfortable with. But I'm using PyCharm because it allows you to set up environments a bit more easily. So yeah. If you want, you can skip this step and run the code directly from the console. Here I'm going to set up an environment using the interpreter from the virtual environment that I recently created. I'm going to select Conda, and here I'm going to pick up the Unray car environment that I just created. Then click OK. Now it's worth mentioning that as you can see, it used Python version 3.10, and it's important that you use that version because it's the one that's currently supported by Unray. So please make sure if it was created with a different version, please make sure it uses 3.10. Okay, now that we have the environment set up, we can start using raylib. So from ray.rlib.algorithms, we're going to use PPO. We'll import PPO config. Now from Unray, which is the library that we just installed, we're going to import the environment. So .envs.base env will import the single agent environment. And we'll also import the spaces. We also need to import NumPy. And we import the Unray configuration as well. Now we're going to create a 10 position array we're going to call high. And we're going to initialize it to be to have a value of 10,000 in each position. And we're going to set the type to npfloat32. Now we'll create our algorithm, which we're going to name ppo_config. And it will be an instance of ppo_config. Now we're going to add some settings so we don't run into issues. First, we're going to set up the resources, the number of GPUs. We'll set it to 0. You can set it to a different number if you want, but it requires some additional installations, so we'll skip it for now. Then we're going to set the number of allowed workers. For that, we use ppo_config.rollout. And we set the number of rollout workers to 0. From here on out, you can tweak the settings, you can play around with it if you want. You can check the documentation to see what the allowed values are. But yeah, we're going to try to keep it simple for now. Now we're going to configure the environment. Which will be a dictionary. It's going to be made up out of our observations. Those will have the type bridge spaces .box, which will be between -high and high, which is the array that we defined in line 10. So this will be an array of 10. Oh, I'm sorry, this should be 7. Will be the 7 observations that we defined with the line traces. Now for our actions, they all will also be of type bridge spaces. Well, bridge spaces, but that multi-discrete, and it's going to be an array of 2 types of actions. So will be one action that has 2 possible values. In this case, it will be the steering. We can have a 0 or a 1, and that will be translated to left or right when we pass it to Unreal Engine. That's the one that we used on this part in the step function, if you remember, over here. So we've set up this action, which can have 2 possible values, and the observations that are these 7 values from our line traces that we can see over here. Now we're gonna set up, now that we have our environment set up, we're gonna create an instance of Unray config. We're just gonna name it Unray config. Next, we're gonna set up a variable for the environment. So for our single agent, so it'll be a single agent environment. We need to pass the configuration and a name. So we'll name it car environment or car env. This is so our lib can register their environments. Again, for more information on this, you can check their documentation. Now we're gonna create an algorithm, call it algo, and then it will use the configuration that we just set up. That configure algorithm, it will take as an input the PPO config object and the environment. And finally, we'll set up our training. For that, we're gonna set up a for loop. We're gonna iterate in a range. Right, you can use a higher number. We're gonna use 20. Yeah, whatever amount you want. And in that loop, we're gonna do algo.train. We can print the iteration to know which phase we're in. And if we want every certain number of iterations, we can save our progress. So here, every 5 iterations, we're gonna do a save. So we're gonna do save result equals algo.save. You can pass a path which you want to use it. If you want to save to a certain path, you can pass it here. Otherwise, it uses a default. And we're gonna print the path in which it saved the progress. And that would be all for our Python file. We could run it from here. I'm gonna run it from the terminal just so you can see. We also have that option. Okay, now that we have our environment ready, one thing worth mentioning is that we need to run our Unreal Engine instance first, and then we can run the Python file. Otherwise, it will throw an error. Okay, now you can do hit play, and you can hit F8 if you want to see the behavior of the car during the training process. Okay, one thing worth mentioning is if you can avoid using the print log or printing to the logs, because it could crash the console and cause issues. So yeah, if you can disable print to log in all the prints that you have. Now you see that the log doesn't have those anymore, so we just have the ones on the screen. Now just to make sure everything is working right, we can add another print statement, and we can print the reward value. So we'll just add a print and hook up the reward. This will be executed whenever we execute a new step. So we do that from Python. If we hit play, you'll see it's not printing it. But when we run the Python script, you'll see the reward value on the screen. Now we can go to our Python file. We can run the file we just created. Yes, as I said before, it's very important that you use Python 3.10. Please make sure you're using that version, otherwise you're gonna get errors. So now we just do Python and the name of our file. Make sure it's running on the virtual environment. And now it should start training. One recommendation is that whenever the training is running, try to avoid manipulating the environment or the agent in Unreal Engine. Since Unray is in beta phase, it might cause crashes. So yeah, please try to avoid manipulating the Unreal Engine instance when it's running. Okay, there was a small mistake in the reward function. So whenever the car is going off track, it's going to the edges of the path, we're gonna set the sum value to 0 instead of -1. And yeah, that'd be all. Okay, in case you run into this error, something you can do to keep your progress is you're gonna go to the last saved checkpoint. You can get the path to which it was saved. So you can copy that path and use it in the Python file. So you can load from that checkpoint using well, the path, and do algo that restore. So you're going to restore the progress up to that checkpoint, and you can also well, start from here and also save it to that same path, so you can keep your progress.